Hello everyone, and welcome to next day, day 4 of exponential logarithmic functions. Today we're going to be looking at kind of a compound interest again to start, and then how it develops into a new and very special number that's also got its own special name and stuff like that. So anyway, let's get into things. So here's the situation we're going to start with. We've got a $1 that we're going $1 that we're going to deposit at a bank, and that bank's gonna be really nice and give us 100% interest. Okay, so how much money then? How much money will we have at the end of 1 year if the interest is compounded? Okay, and you'll see we have different options for our compounding interest here. So I've got 4. What happens if it's compounded just once at the end of the year? What happens if the interest is compounded twice? So once halfway through the year, once at the end of the year. What happens if it's compounded monthly? That means at the end of every month, right? And what happens if it's compounded daily? That means 365 times. Okay. So again, with the yearly or annually one, that's that simple interest formula that we talked about, where we just take our initial amount there, multiply by 1 plus r, our interest rate as a decimal is 1, and we get $2 at the end of the year. Okay. Now, the next one though, semi-annually, okay, so that means we're going to compound the interest, right? So this one was actually like simple, technically, okay, because it was compounded just once in the year, and the interest rate is, yearly. But this next one, right, this is a compound one, and all these other ones here are compound. Okay, because we're doing it more than once, so we're growing interest on the interest. So, I actually calculated it out for this one. You can see the full calculation. I didn't use the formula, compound interest formula, for this one. So the mid-year formula, okay, would be, our initial dollar there, plus 1 times 1 plus 0.5. Again, if we're doing it twice in 1 year, you have to divide that interest rate up into 2 equal parts, so 50%, right? So that's 1 plus 0.5 there. And that gives us $1.50 halfway through the year, right? Then at the end of the year, well, we get that one more, 50% interest, compounded on the original that we had right there, and we end up with 225. So you can see here, in comparison's sake, right? Semi-annually gives us a little bit more money than that's yearly does, or annually. Looking down, next one at monthly, right? So now we're going to take this 100% and divide it up into 12 sections. So we're going to do 1 plus 1/12 there. Again, 1 being the decimal for 100%, dividing it by 12. And we multiply by our initial investment there of $1. And so for that, at the end of the first month, we now have $1.08, 33333 repeating kind of thing forever. Okay, and we can do after at month 2, we take that $1.08, 3 repeating, okay, and multiply again by 1 plus 1/12, another, 1/12 of that interest, and we're now at $1.17 is how much money, that would be, the investment would be worth. Continuing on continue on to the end of the 12th month, okay, I just went ahead and used the formula there for that. So again, our initial investment, r divided by n, so 1 divided by 12, and then time to the n times t, so n is 12, t would just be 1 year there, and we get $2.61, which is more money than semi-annually and more money than the yearly. Okay, and then finally I also did daily too, so you can see the 1 over 365. Again, I didn't write out all the days, that would be quite a bit there, and I just ended up using the compound interest formula. So again, initial investment principal $1, right? Our interest rate was 100%, so 1 is a decimal, 365, for that number of times compounded, and then 365 times time, which is just 1 year, so 365 is the exponent there. I get $2.71. So what conclusions can we draw from these results? Well, the results that we can draw, or conclusion we can draw, is that the more we compound, right, if you hold everything else constant, if you keep the same investment, if you keep the same interest rate, and if you keep the same length of time for that investment, okay, the more you compound and in a given time period, the more money you get, okay? So then, we went from once a year to twice a year to 12 times a year to 365 times a year. What about an infinite number of times in a year? Okay, which would be like continuous, right? Whoops, which would be like continuous. Wow. Hot mess here. Okay, so you're like continually earning an infinitesimally small amount of interest that would eventually sum up though to that 100% interest rate that you do get, after the end of the year. So what does that look like? Well, it would be like our n, right, number of times compounding, it would approach infinity, right, with our formula. But what does that value approach? Well, another way to write that is saying the limit as n approaches infinity. This is another way of, just different notation for the same thing as this is saying. Okay, what's the limit as n approaches infinity of this compound interest here? Well, the answer is the number e. Okay, so e is an important number, just like pi, just like I, where it's so important that it actually has a letter that designates to represent it. The decimal value of that is approximately 2.718281828459. You can see it on your calculator if you press second divide by, or it's also there at second ln, which is next to the number 4. Okay, you can get that number. Okay, so that's E. It's also called the natural base. Okay, natural because it shows up in nature, also because it's got some very interesting properties in calculus as well, where the slope, and specifically for the natural exponential function, where we take that e and raise it to the x power, where its slope, its rate of change is the same as the value of the original function, which is kind of unique to e to the x and only e to the x. So let's graph this thing. Again, it's an exponential function, so it's going to look just like 2 to the x. It's going to look just like 10 to the x in shape. You know, obviously the amount of increase is going to vary slightly. It'll look more like 2 to the x than 10 to the x because e is closer to 2 than 10, you know. But anyway, you get the idea. Okay, so let's just graph this. I already actually made the table right here. Again, you can use your graphing calculator for this because, again, there are going to be some nasty decimals, so it's just much easier to use your graphing calculator. All right, so 0, 1 is going to be kind of like our, important point there that gives us nice numbers. But then for like 1, 2.7, we're just going to like eyeball that. And 2, 7.4, again, just kind of eyeball that. And then -1, is about there. And -2, we get 1.1353, so right there. So again, connect these dots. And there's our typical exponential growth curve. Okay, domain still -infinity to infinity. Range, what's the lowest y value? Well, it's going to be 0, right? It doesn't get down to 0 though, so put that parenthesis there next to it, and it goes up to infinity. And the HA, horizontal asymptote, is going to be y equals 0. Again, you can kind of see it very clearly here. We're not going to cross that x-axis. Okay. So then let's see some problems we should be able to do. So, for example, here we should be able to sketch a graph of this function. Okay, with some transformations there. So right away we can see that that +1 means we are shifting left 1. That +4 means we're going to be going up 4. Okay, and the 3 means a vertical stretch of 3. Okay, so again, in my previous table, and the typical exponential function tables that I have you guys do, I have you use -2, -1, 0, 1, and 2 as your exponents. You don't have to use those. Again, this one definitely you can use a graphing calculator for because of the decimals and stuff, but we'll just do that. Since everything is shifting left 1, though, I'm going to go ahead and shift all these x values to the left of 1 as well. So we'll get these x values. And again, you can type this into your calculator. Okay, I am not going to show that you guys know how to do it in your calculator. Just make sure you type it in correctly. Again, you can access this e on your calculator either using second and then the divide by button, or second and then ln, and ln is next to the 4. And we'll talk about ln a little bit later there, what that means. Anyway, so I'll just type this in here real quick into my calculator. Go to my table. Okay. And so let's see here, I get about 4.4 here, about 5.1 here, about, well, exactly 7 here, about 12.1 here, and about 26.1 there. Or 26.2, I guess, is what I should really round that to if I'm like doing good rounding. Okay, I'll just plot the points. So -3, sorry, that +4 there, right, that indicates we're going to have a horizontal asymptote at 4. So I'll go ahead and just draw in the horizontal asymptote, right? Our normal horizontal asymptote is at 0, but since we're shifted up 4, we're going to have our asymptote at 4. Let's see here, so -3, 4.4, so I don't know, like right there, we'll say -2, 5.1, so like right there. We'll say -1, 7, so like right there. 0, 12.1, so like right there. I already have the point from a previous time I did this. And then 126.2, well, you get the idea. It'll be like, oh, I don't know, it's not there somewhere. So again, we can kind of ran out of space. Okay, and then voila, there is our curve. Okay, domain is -infinity to infinity. Again, no problems with any of our x values there. We can't really be undefined here or anything like that. Lowest y value is not going to be 0. It's going to be 4, right? Because we shift everything up 4, and it goes to infinity. And the horizontal asymptote we already said was y equals 4. Okay, so again, there's your graph. No big craziness going on there. All right, last thing here, of course, we should also be able to write the natural exponential function given a graph of it. So we're going to do that here too. Again, understanding that our typical exponential function, which the transformations look something like this. Okay, again, where A is the vertical stretch or shrink, H is the shift left or right, K is the shift up or down. Okay, and again, you can see here we got 2 points that were given. I would strongly encourage you to to determine the shift right or left, use the nicely numbered point, right? If you remember here, okay, you know, this nicely numbered point came from, you know, the left one shift, right? That was normally our nice point is at 0, 1. Okay, the x-coordinate 0, it got shifted left 1 though to now be at -1. So use the nice number point there to identify that shift left right kind of transformation. So in this case, right, the 4 means we are shifted right 4, and the asymptote is at +4 as well. That means we're also up 4 as well. Okay, so just like that. Okay, those will indicate to us. So we have y equals a times e to the x minus 4 plus 4 like that, and it's just a matter of figuring out what a is now. We're going to use this other point to do that. So we'll just plug 2e plus 4 in for y and 5 in for the x. And now we solve. So we'll subtract 4 on both sides. Those 4 will cancel. So we'll have 2e equals a times e. Now 5 minus 4 is 1, so it's e to the 1, which is the same thing as just e. So 2 times e equals a times e. Divide both sides by e. So the e's cancel. And we have a is, hey, 2. So y equals 2 times e to the x minus 4 plus 4. And that's our equation for our exponential function there. Okay? So that's our graph. I'll give you guys some homework problems, probably one graph and one writing the equation from the graph too. One other thing I wanted to briefly mention here, just about our exponential functions. Okay, this number e, I did want to show you here. I actually wrote this, you know, we can actually evaluate this limit numerically using our table and our graphing calculator. We don't know how to evaluate this any other way right now because we don't have, you know, calculus and stuff like that. We can evaluate it using a graphing calculator. I'll just show that to you here real quick. So you can see I already typed in excuse me, the function there, okay, that compound interest function, right, for our $1 investment, that's 100% interest rate divided by x, and we're going to have that x approach infinity, right, because the x is in the place where the n would be, which is the number of times compounded. If we go to our table, you can see here that as our numbers, as x or as n, the number of times compounding grows, you can see that we are getting closer and closer to that, you know, e number. Okay, here you can see it's very close, 2.7182818283. I think it's supposed to be a 4 instead of a 3 there. So you get the idea. Okay, it does approach that e value. And again, that's the best we can kind of do with what we know right now. Okay, anyway, that's the end of it. We'll stop there. Thank you guys. And we're going to use this e from here on out. Okay, so when you see e, think this number right here. That's the natural base. Okay, thanks guys. If you have any questions, message me or comment on the posting. Bye.